It's a general argument. Suppose I had two Turing machines. We were equivalent. And one of them belongs to K. Well, it belongs to K means the language of this defined by this machine is nobody, the empty set. Belongs to K means the language is empty. Okay, but then this means the language of T2 is empty because they're equivalent. Right. Well, if the language of T2 is empty, this means T2 belongs to K. That's it. So if you have a Turing machine in K, and you have another one who is equivalent to it, C will also belong to K. That's the argument.
So we have
You probably, it's obvious in this case.
don't we have to find two Turing machines like this?
Two specific ones that are equivalent? No, you don't have to.
Oh, to find one.
Why you have to find two specific ones?
Oh,
Even if you found them, I don't even, suppose you have in your paper, in this page, one machine, the other machine, and they're equivalent. Suppose you were able to prove it, which is hard, because this is an undecidable problem. I write down another undecidable problem for you. Language, yeah, language of M1, equivalence of Turing machines.
Undecidable.
It's undecidable. There is no algorithm. If you give me two Turing machines, there is no filter, no algorithm I can feed them into. And out comes the outcome. Yes, they're equivalent, or no, they're not equivalent. There is no such algorithm. But suppose ad hoc, as a human, for those two specific machines, he has one on this page, that one on this page. She made a very fancy argument. She proved those two are equivalent, right? So, and they have the same language, and one of them has language the empty set. Without going to look what the machines are, I know the other one I know the language of the other one, don't I? The language of the other one, if they're equivalent, it will be the empty set. So I don't need to know the specific machines. As long as I believe what she tells me here, I can conclude the other one has the empty set. So why do I need to know specific machines to make this argument? This is a general argument. No matter what the machines are, if they're equivalent, and one has the empty set, the other will have the empty set. Okay, that's it. So the answer is no, you don't build specific machines here. What good is this?
So what does this T2 we built here tell us?
Like what?
Okay, we built T1 which says no for everything, and then T2 which says
Yeah.
yes for everything.
Yeah,
So,
why?
Yeah, why do we...
No, that was the first step. Rice's theorem, before he can conclude the language is not Turing decidable, he wants to make sure the language is not the empty set, and it's not the universal set.
One Turing machine which satisfies the property and one which doesn't satisfy.
Right.
Yeah.
That's why you find those two examples in the first step, because he wants to make sure this set is not the universal set. If it was true, every Turing machine had this property, then it will be decidable. For example, if I tell you, take the Turing machines, instead of saying language empty, that have $1 at the start of the tape. Is this problem decidable? take all the Turing machines, right, where they have this start of the tape marker at the start of the tape. Well, by agreement, here, we said always at the start of the tape, you have the $sign, whatever, the marker. So, is this problem decidable?
Yes.
Yes. If I show you a Turing machine and ask you, does it have the dollar at the start of the tape? Yeah. So, you can put any property you want here. Right? So, that's why he has step 1. If every Turing machine has this property, of course it will be decidable, like in my example. I can say, therefore, it's not decidable. It is decidable. Or, if I say, what's the property here? Take all the Turing machines that do not have a marker at the start of the tape. That's the property. Well, by agreement in this class, we always, the marker is there. The tape is initialized. You have to do the factory like that, you know. That would be the empty set. Take all the Turing machines where they don't have a marker at the start of the tape. That is the empty set. Is this problem decidable? Yes. If I show you a Turing machine and ask you, does it belong to this set? Can you decide that, yes or no? You say no. You will have a marker, this is not there. Also, this is the complement of the previous set. The complement of a decidable is decidable. So that's why you find those examples. You try to verify that's not the case where everybody has the property, or it's not the case that nobody has it. Because in those cases would be decidable. Okay. All right. So based on this, you say, therefore, that's number 2, it's not decidable. Therefore, by Rice's, K is not decidable. And whose language is regular. Do you have an algorithm so that when they give you a Turing machine, he will decide if the language is regular or not? Another way to say this, given you a general program, do you have an algorithm to decide if this general program is equivalent to a finite state automaton? It's equivalent to a program with only if statements, no stacks, no data structures. Right? Only variables and if statements. Okay. No. The idea is, can I reduce any general program to a simpler program? No. Which is FSA. And there's no algorithm for doing this. This is undecidable. How would you prove it? Rice's theorem. Okay, the second step usually is pretty much the same, because if you have two machines with the same language, and one is in there, this means its language is regular. Well, if they have the same language, the other one will be regular, which means it will be also in there. Okay. Where you might have to work harder here is find one in there, find one whose language is regular. The one you gave me that says yes to everybody, the language of that Turing machine was sigma star, which is regular. So that will be an example of a language of a Turing machine that is in here. Okay. Find a Turing machine whose language is not regular. Now it becomes harder. But you could give me one you already know.
Context.
ANBN. Give me a Turing machine for ANBN. We actually built one for ANBN CN.
Right.
But we can build one for ANBN. Or I could even use the AN, B, and CN because that's not regular either. Or build one for A and Bn, which is easier than building for A and B. Instead of 3 loops, the A's, the B's, and C's, I have 2 loops. Similar. Whatever I put here, context free, whatever, you can make the same argument. It will not be decidable. Whatever this property is. If the property is about the language of the machine, usually it will not be decidable. Take all Turing machines. Which halt in 2 steps. Or I would say 10 steps, whatever, I give you a number. Let's say 2 steps. Is this problem decidable? See, the property now is not about the language. I'm not talking about all the Turing machines whose language has this property, right? Rice's theorem will not work now, right? Because if you have 2 Turing machines with the same language, and one is in here, this machine will have it in 2 steps. Well, it doesn't mean the other one. The other one might do the same problem in 10 steps. I can take any program, and stick superfluous statements in there. Say, x equals 1, x equals 1, do this 10 times. X equals 1, x equals 1. Well, that took now 10 steps, you know, for the same. Right? So, Rice's argument will not propagate here. Is this decidable? Sure, it's decidable. Do you have an algorithm so that when they give you a Turing machine, a program, the algorithm will determine if it stopped in 2 steps or not? 2 steps means execute 2 statements. Sure, here's the algorithm. Take your program, after each statement, stick count plus 1 to count the number of steps.
Run it.
What?
Run it and then determine how many steps it takes.
Yeah, definitely.
But that can be a, I mean, Turing machine which doesn't have this property, so we can use the right.
A Turing machine that does not have this property?
We write
Yeah, there could be a Turing machine, no matter what. Now, here I was not specific, right? I say it halts in 2 steps. What do you mean halts in 2 steps? It depends on the string, right? If you give me this input, it might take 10 steps. If you give me the other input, 20 steps. Give me this input, 2 steps. Right?
So we have a machine that has this property and one that doesn't have this property. So
no, I'm not trying to do Rice's theorem. I'm not trying to find one that has this property.
But why are we not doing it?
Why we're not doing Rice's theorem here? Because it will not work.
We already have a machine that we can write a machine which does the same thing in more than 2 steps.
Yeah, sure, we can do.
So that was the first condition.
Yeah, you can do the first condition. You can find one that will halt in 2 steps. Here is one. Go right, halt. Okay. This always halts in 2 steps. No matter if you have blanks, A's, right, okay. Yeah, sure, you can do one that does not halt in 2 steps. Do right, 3 times. It halts in 3 steps. Okay, so what?
So first condition.
Okay, sure. And now the second condition. Okay, try to do the second condition.
Just like before we can...
Well, tell me.
First
okay.
one,
so take 2 Turing
one
machines.
which has 2 steps. We have
take 2 Turing machines that have the same, define the same language.
First one has 2 steps. And it decides from the property, so obviously the second one also shows it.
Why obviously it will also have 2 steps?
The language
for the same input.
The language will not be correct.
Just because the language is the same, it doesn't mean the other one will have in 2 steps.
Oh, okay, here the language may not be the same,
Yeah.
even though it has.
No, the language is the same. Yeah. Whatever the first machine says yes to, the second machine says yes also. And when the first machine says no, the second says no also. Right? But if for a string, if the first one does it in 2 steps, why the second one will do it in 2 steps? Okay, how do you know that? Okay, here. Okay. What will this machine do? If you are here, she will go 1, right, right. She will stop here. What will this machine do? If you are here, right, left, right. These two machines do the same thing. But in how many steps did this guy do it? In 2 steps. Going right is like x equals 1 statement. But this guy did it in 4 steps. I can do the same thing in 6 steps, in 8 steps. Right? You're not, Turing machines can achieve programs, as I said, linguistic statements that do nothing. They are not involved in the input, they are not involved in the output. Take any program, pick a new variable. Somebody told you, you have a set of dominoes and they are labeled. Okay? One side has a string, the other side has another string. For example, let's take an example. One side is a B, the other side is CA, that's the first domino. Like small wooden pegs, Then A, BA, one side is A, the other side is BA. CAA, and ABCC. So you get those 4. Okay. All right. Now here is what I'm asking you to do. Can you put them together in a sequence? Okay. This sequence could be infinite if you want. You have the ability to repeat the dominoes if you want. Like I can put this twice, then I'll get BB, CA, CA. Repetition is allowed. If you want to.
What is this domino and follow?
Okay, forget the word domino. Think of them as fractions.
Okay.
Like 3 divided by 4.
Okay.
Well, instead you have string divided by string.
Okay.
String on the numerator, the string on this side, string on that side. Okay. Or here is a domino, this is a domino.
Okay.
And up here you have B,
Okay.
and down here you have B, C, on this
okay.
side. Okay. Now, your job is to put them together. And you can put it this way or that way, right?
Oh, okay, okay.
Oh, I'm sorry, no. The tops have to be, they're different color, okay?
Okay.
So you have to put them together with the black under and the stripes on top. But so you have to make a sequence of them,
Okay, all sets.
okay? But obviously I can make a sequence real easy. Just put all 4 next to each other. But the sequence must have some properties. Okay, construct a sequence such that the numerator sequence as a string is equal to the denominator sequence as a string. Such that numerator sequence equals denominator sequence. One side equals, top side equals downside. Probably if James, if Tony was here, he would have actually the visual. He was going to have 4 dominoes, and he would give it to her. I said, okay, put them together, and she will try. All right. Okay. Okay, so it sounds easy enough. Okay. Well, who can solve this? Can you put them together somehow so the top sequence is equal to the down sequence?
We can't use the 4th domino.
Hmm?
We can't use the 4th one, ABC over C, because there's no way to get BC below.
I have a way to use it. Remember, you can repeat. You can use one domino, the same domino, more than once. Is the key. You might have to. In some cases, you might have to. Are you thinking just using 4 of them?
No, no, no. I'm just saying. Well, at the top on the top of the 4th domino, we have ABC, but
Yeah.
the only place where B is on the bottom is in BA, and
Okay,
you
so
can't
how
get C
about,
after
how do you get C? Oh, let's see. CA, oh, you know, you're right. You know why this is happening? Because I flipped this. He's right, there's no way. So for this one, there is not much. And he just proved it. There's no way to do it. Right? Because to get BC, there is no way to get BC. There is only one B, and then no matter how you put them together, the B will be followed by A in the down. Right? So, but in the up, you have BC. Okay, what I should be here is AB. Okay, so let's try this one. So this one has no match, he's right. Now let's try this one. I just changed the BA to AB. Is there a match? Well, if you can try as human, you know, or you can try to find an algorithm. Okay? If you find an algorithm, how would you do it? Using 4 of them. Maybe I can. So let's try 1, 2, 3, 4. 1, 3, 2, 4, 4 factorial. All the combinations. Right? If one of them works, you stop and say, I got it. Okay? But let's say nothing works. Here, nothing will work. Okay? Then you say, well, I can allow repetitions. Okay, so repeat 1 at a time. So instead of 1, 2, 3, 4, I'll try 1, 1, 2, 3, 4. Okay. 1, 2, 2, 3, 4, you know. 1, 2, 3, 4, 1. Okay. 1, 2, 1. Oh boy. So you have to take 1, 2, 3, 4, and then you have to stick a 1 in all possible places. Okay. There is combinatorial explosion here, but you will keep going like that. Nothing works. Right? Try to have 1, 2, 3, 4 with 2's repeated somewhere. Okay, you tried a repetition, one of them 2 times, nothing worked. You will try a repetition of one of them 2 times, but the problem is, when will you stop to go back repeating 2 of them 2 times? If you're going infinite this way, you cannot stop to go that way. But especially if there is no match, you are in serious trouble, you know, because no matter what you try, you can try up to infinity, obviously, if you allow repetitions. And you will never, the algorithm will have an infinite loop in it. You cannot do it. Okay? So it seems easy, but it's not so easy if you want to write a program for it. Actually, it cannot be done. This problem is not decidable. deceptively simple to describe the problem, you can give it to a child, say, do this. He can do it sometimes. But if you want to write a program for it, it cannot be done. Forget it. It's not decidable. Start with A over AB. Well, then you must, the next domino you should get, it must start with B. Okay. So it has to be this guy. So far you have AB. Now the next one must start with C. Okay. Which is this guy. So you have A, B, C, A, B, C, A here. So the next one must start with A here. You have two choices. Let's try A over AB. A, B, C, A, B, C, A. The next one is AB, so you must start with AB, so take this guy. A, B, C, C. Oh, yeah. The sequence terminated and you have a match top bottom. So that's a possible solution. And the guy who give them a combination, and the guy who does it in the shortest time, he wins, you know. You have the post correspondence problem champion of the world, you know. It's a bit complex. What?
So this is undecidable.
This is not decidable yet. You cannot write a program for it.